Hi, my name is Mike George. I'm the head of product at CERTORA, and today I want to talk to you about our technology for verifying smart contracts and hardening them. What we do at CERTORA, we have a tool called the CERTORA Prover, and it checks your program against the specification and tells you whether your smart contract does what it's expected to or not. So our tool takes in your EVM bytecode, as well as a specification that's written in our custom specification language. And the specification says, here are properties the contract should have. You know, the contract should be solvent, for example. Or certain methods should not revert. And our prover takes in these two things, the smart contract, the EVM bytecode, and the specification, and it outputs one of two things. If you've done a good job on your contract, it'll output a yes, saying, yes, under all circumstances, your contract does satisfy the property that you've said. And if it turns out that actually you have a bug in your code, the prover will output a no, and not only will it tell you no, your program does not meet its specification, but it will also give you a specific example. Here is a state that your contract can be in. Here is a method that you can call in your contract. Here are arguments for this method, and if you call this method with these arguments in this state, then this will violate your property. Okay? So I want to show you a little bit how you would use the prover. And to do that, I want to walk you through a bug that CERTORA found in Sushi's Trident protocol. And this was a bug that actually would allow you to completely drain a liquidity pool. So it's quite an important bug. And I want to show you how we think about verifying contracts. So let me first tell you about the contract example. So it's a constant product pool, which is a liquidity pool. It holds two types of token. I've called them token A and token B here, in reserve. And it allows you to swap one kind of token for the other. Okay? So let's say Buffigwe comes along here and says, I want to buy 10 B tokens. We have to figure out what the price of those B tokens is in A tokens, because they're swapping. So if they want 10 B tokens, they need some A tokens. And the way we figure out that price, that's where the constant product of the constant product pool comes in. So after this transaction, there will be 10 B tokens in reserve because 10 of them went to Buffigwe. And to keep the product constant, that means there needs to be 10 A tokens afterwards as well. And that means that Buffigwe needs to spend 5 A tokens to bring the number of A tokens up to 10. Okay, so that's how the constant product pool works. This has the effect of making rarer things more valuable. Okay, and of course, I want to show you one other thing you can do with a constant product pool, which is maybe Buffigwe doesn't want to trade, maybe they want to actually invest in the pool. And the reason they would want to do that is they get some liquidity tokens, right? And so in the pool, originally other investors held 10 of these liquidity tokens. When Buffigwe invests, they're going to get 2 liquidity tokens. And afterwards, the reason I show this is the product here isn't actually constant, right? If you invest, both sides of the equation go up, and so the product's going to go up. But also the number of LP tokens in the pool goes up. And I just want to point out, to make the math work out, the number of LP tokens squared should be the same as the product. So before it was 10 times 10 is 100. After it was 12 times 12, 144. Okay. All right. Now, in my former life, I was a teacher, and so I can't resist putting a quiz in the middle of my talk. So if I asked you to describe a key property of constant product pools, what a lot of my students would say is the product is constant. And that's a good answer. And of course, we know the product of the reserves is constant depending on the size of the pool. Right? So if we think now about a smart contract that's trying to implement this constant product pool, we might have an interface. It might have different ways to get the amounts of reserves, the total supply of LP tokens, different ways to swap, buying A or buying B. You can mint and burn. That would be adding or removing liquidity from the pool. And the thing that we care about, again, is the product of the reserves is constant. And with this interface, we can actually write down an expression for that. The reserve A times reserve B is going to be equal to the total supply times the total supply. That's what I told you on the previous slide. So now I want to think about how would we actually check if we have a smart contract, how would we check that it has this property? This is like the defining property of a constant product pool. So one thing we might do, and one way that a lot of smart contract developers find bugs, is they think really hard, or they hire auditors who are very good at looking at Solidity code or bytecode and finding mistakes in it, right? And in this particular case, I've shown you a little bit of the Trident pool code that, in fact, the bug is somewhere in this method. I'm not going to ask you to even try and read it. You won't find the bug. Maybe you will if you're really good. You probably won't find the bug right away. But the point is, this is just a piece of the code. There's about 550 lines of Solidity code that contains this particular bug. Auditing is a manual process. You never know if you're done, if you've missed something. And so that's difficult. It's important, it's useful, and actually I should mention the bug I'm talking about was found independently by an auditor. So it's not impossible, but it's difficult. So another thing that developers often do, and is a really important tool, is testing. So what you might do, again, if this key invariant is what you want to check, you might write some test code, right? And at the end, you're gonna do some things, right? You're gonna set up your pool, you're going to call some method on your contract, and then at the end, you're gonna check exactly the property you want to check, right? So reserve A times reserve B is the total supply squared, right? But the question here is, if I want to write a good test suite, what am I going to put here, right? So I've written good comments, right? I'm going to set up a pool, I'm going to call a method. But what method am I going to call? Well, I probably want to call all the methods that do, various things, swap and burn and mint and so forth. But even then, I'm going to have to call them with arguments. How much am I going to have to swap? How much am I going to have to burn? I can get to the point where I have 100% coverage, but maybe there's a bug that's caused by some overflow or something like that. So even if I have 100% test coverage, I may miss a bug just using testing. And more than that, it's not just the method you're calling or the arguments you're passing. The actual state of the contract before you actually execute the method, that matters a lot too. Maybe the bug only shows up if the pool is currently empty, or maybe it only shows up if the pool is right above its minimum LP supply, or who knows, right? So once you start thinking about, okay, let me list out all of these scenarios I care about, and then start writing your testing, you're going to have a lot of testing. And again, it's manual. It becomes a more automated, but still manual process, right? And to figure out good cases, you're actually back to looking at your 550 lines of code to figure out what are the different paths you care about. So let me tell you how we would do this with the CERTORA prover. So as I told you, the CERTORA prover takes in a specification. What should your contract do, as well as your contract, and it checks to see what it does. So with the CERTORA prover, the way we would check this invariant is we would write the following specification. Invariant constant product, that's the name I came up with. The product of the reserves is the total supply squared. And that's it, that's the specification. Now, it actually turns out we did some of this verification. We ran the tool. There are some cases with some round-off error where this is actually not quite true. It's true like within epsilon. But we can also have a simpler invariant that should definitely always be true. So this invariant, this modified invariant just says if either of these is 0, then the total supply has to be 0. So if the reserve A is 0, total supply has to be 0. Reserve B is 0, total supply has to be 0, right? So it's just saying the left-hand side is 0 means the right-hand side has to be 0. Okay? So we can write down invariants like this in our specification language, and then the prover will check, does the contract obey the invariant? And it checks it no matter what. So it tries every possible method and every possible code path in every method with every possible argument, which sounds impossible, and it's a little bit magical. What actually it does is convert the contract and the specification into a logical formula, and then use SAT solver to actually show that that formula does hold. But effectively, the prover checks that your contract obeys the invariant no matter what, and if it doesn't, it will provide a counterexample. It will say, here's a state of the contract, here's a method you can call, here's an argument to the method, and if you execute that, then after that method call, this invariant will break. Okay? So I'll show you a little demo here. So let's say I go to demo.certora.com here. So you can actually see here, we have a whole bunch of examples where you can see some Solidity code, you can see specification. You can put in your own Solidity code. If it's small enough, it'll just work in the demo site. So I'll go to interesting bugs here, go to the constant product broken. So here we have, this is actually a simplified version of the contract because there's some setup we had to do to get the actual contract to work with our tool. But this is, for demo purposes, contains the same bug. And here, this is probably a little small for you to see, but that invariant that I showed you is right here, that second invariant, integrity of supply. There's a little bit of setup we have to do as well. So for example, we don't want the prover to give us an example where you start from this impossible state and then you do this operation. We don't care about that. So there's a little bit of additional setup. But to first order of approximation, the invariant looks just like the invariant I showed you on the previous slide. And so you can click Start Verification. It takes a couple minutes. I mean, it's checking a nearly infinite number of, oh, it doesn't because it's cached, but it does take a while. But let me just show you the results in my slide. So what you would get as output from the prover is all of the methods of the contract are checked. And we find that most of them do actually preserve this invariant. But there's this one method called burn single that actually violates the invariant. And not only do we know that this burn single method violates the invariant, but we get, sorry, trying to scroll on my screenshot, didn't work. We also get a call trace, and we can see here actually that the burn single function gets called, and by drilling down, we can see the different arguments, we can see the state of the storage of the contract, and we can find out exactly what happened. And then using that, of course, then it takes some expertise to say what's the actual bug in the code. But knowing there is a bug and you can exploit the bug with this following test case is a really helpful thing to be able to do. So that's what I wanted to show you. The CERTORA prover can check a lot of different things. So I showed you an invariant. You can also check things. You can write down method specifications. If you're writing a smart contract, you probably put some comments that say, this method, transfers 10 X tokens to whatever. You can actually write a rule that checks that the method does what you say. You can check properties like solvency. If I might have to pay out, X tokens, I can guarantee that I actually have X tokens allocated to this contract. You can check things like permissions, that users can only change their own balances and not the balances of other users. Or even things like front running. You can check properties like, if I take this transaction and insert another transaction just before it in the same block, the price that I get will be unaffected. You can write rules like that. And many other things. It's a very flexible language. So I encourage you to take a look at our demo site, demo.certora.com, or drop us an email. And that's what I wanted to tell you. Thank you.